In this lesson, we're going to be looking at oscillations and waves, from which we started looking at them in Form 3, where we introduced the basic concepts of oscillations and waves. Following our syllabus, we are supposed to look at electromagnetic waves, light, and lasers. So, in today's lesson, we'll be looking at electromagnetic waves. So, we learn the meaning of a wave, where we said a wave is a disturbance that carries energy from one point to another without transferring particles of the medium. So when you say a wave, it's just a disturbance. It just disturbs the medium so that it transfers energy from one point to the other without affecting the particles of that medium. What mediums are we talking about? It can be the three states of matter where you have air, where you have gases, liquids, and solid. So any of these ones can be a medium. So a wave just transfers the energy from one point to the other without transferring the particles of the medium. So an electromagnetic wave is produced from both electric and magnetic fields or effect. Looking at the term electromagnetic wave, you might observe or think that the term electromagnetic comes from two words, which is electricity and magnet. So it's just a combination of these two words forming electromagnetic waves. And here we're even saying is produced from both electric and magnetic fields or effect. And the electromagnetic waves are also known as electromagnetic radiations. So down there having the examples of electromagnetic waves which are included in the electromagnetic spectrum, which we are going to be looking at. So the examples are we have light waves, radio waves, infrared waves, microwaves, ultraviolet waves, X-rays, and the gamma rays. Let's have a look at the said electromagnetic spectrum. So what is the electromagnetic spectrum? The electromagnetic spectrum is just the arrangement of the electromagnetic waves in a particular order. So it is a continuous range or arrangement of these electromagnetic waves that can be arranged in order of their increasing or decreasing wavelength. So we can arrange them in an order as long as you are arranging them based on any characteristic, which may be the wavelength and sometimes looking at the frequencies. So if you arrange them depending on their frequencies or wavelength, we form what is called an electromagnetic spectrum. So we are saying the shorter the wavelength, the more the energy it carries, and the longer the wavelength, the less the energy it carries. So the energy comes in about the frequency. When you say the wavelength, remember in Form 3 we discussed that a wavelength is the distance between two successive phases of a wave or an oscillation. So between any two successive phases, we have the distance between any two successive phases will form what we call a wavelength. So we're saying the shorter the wavelength, the more the energy it carries. So we learned that waves with a shorter wavelength, they usually have the higher frequencies. So if the frequency is high, that means the more energy it carries. The longer the wavelength, which means the lesser the frequency, the less the energy it carries. So this is the full band of the electromagnetic spectrum, whereas we have arranged the said examples of the electromagnetic waves in a particular order in terms of their wavelength and frequencies. So looking at the values which are on top there, that is their frequencies. That is their frequencies. So we're having we're having the numbers which are on top there. So here we're saying increasing wavelength. I mean this is their wavelength. So we're saying increasing wavelength. Here we're saying going from radio waves going to the gamma rays, we're decreasing wavelength. Whereas when you start from this side going this other side, we're increasing wavelength. So if you're increasing the wavelength, that means we're decreasing the frequency. If you are decreasing in wavelength, we're increasing again the frequency. So this is a full arrangement of the electromagnetic spectrum. So the one with the longest, the one with the shortest wavelength, it is the gamma rays. The one with the longest wavelength, it is the radio waves. Also note that There is no sharp boundary between one radiation and the next, as it is in a continuous spectrum. So the spectrum which we have just looked at, it has no sharp boundary between one radiation to the other, in the way that these radiations they may also interfere or mix with each other. So the different wave changes gradually from one to the other waves. Let's have one example about it. So we're having yeah, this is just a breakdown of the electromagnetic spectrum. So we're having the gamma rays, the X rays, the ultraviolet, also called the UV light, the visible spectrum, infrared, microwaves, the radioactive waves. So as you can see, we're having each particular wave or radiation with its own frequency and wavelength. But now we can see that they can change from one wave to the other waves. So they can even overlap, as you say down there. So they can overlap, meaning to say you can have X rays and gamma rays. Here having X rays and gamma rays. So you can have X rays, gamma rays, and even UV rays with the same wavelength, maybe on the different frequencies and even similar frequencies. Why is this so? Because there is no sharp boundary in the electromagnetic spectrum. Hence, they can overlap and their properties or wavelength and frequencies they may change abruptly. Yeah, so they may overlap, which means we can have two or three radiations having the same wavelength and the same frequencies. Let's discuss the wavelength, frequency, and energy in an electromagnetic spectrum. So we started looking at wavelength. So wavelength in an electromagnetic spectrum, the range of wavelength is huge. The radio waves have the longest wavelength, which is in kilometers, while the gamma rays have the shortest wavelength, which is less than 1 billionth of a millimeter. So as I said earlier on, the gamma rays they have the shortest wavelength, whereas the radio waves they have the longest wavelength. Let's look at frequency. So the electromagnetic waves with the longest wavelength have the lowest frequency. We have discussed this one. While the electromagnetic waves with the shortest wavelength have the highest frequency. Whereas I said the frequency of the wavelength affects the energy for which the type of radiation or wave transmit from, transmit in a particular medium. Let's have a look at the energy they carry. So the electromagnetic waves with the longest wavelength and the lowest frequency have lowest energy. For example, we are having radio waves, while the electromagnetic waves with the shortest wavelength and highest frequency have highest energy. For example, we have gamma rays. So the secret here is that if we are talking about wavelength, if you have said the wavelength is short, that means there is the highest frequency. If you have said the wavelength is long, it means there is short frequency. That is to say, from there on, let's discuss the sources of electromagnetic waves, not electromagnetic spectrum. It should be the sources of electromagnetic waves. So electromagnetic waves they are emitted when electrically charged particles change energy either from low energy to high energy or from a high energy to low energy. So this is an example where some of these radiations might form from. So we're saying they're emitted when electrically charged particles change energy. It might be either from low energy to high energy or from a high energy to a low energy. Let's have an example of a nucleus. We all know how a nucleus is formed and how it looks like. Whereas it has a center orbit, a center part which is called the nucleus. Then it has some cellular rings which orbit around the cellular path called the shells or called the shells or the electron shells. So whereas in the shells you find the electrons, whereas in the nucleus you find the neutrons and protons. So it may be the electrons being moved from the high energy level. Mind you, the ratios also called energy levels. So they may move from the high energy level to a low energy level, or from a low energy level to the high energy level. So these electrons which are moving or they're changing their energies, they emit these radiations. We also have another example. Yeah, it's just a very same thing we're just explaining it. This usually takes place in atomic structure. When electrons move from one energy level to another, energy is released in form of electromagnetic waves. So the energy is released from these atoms that with their electrons moving from one energy level to the other, and they release the energy in form of electromagnetic waves. That means they may either release the gamma rays or all the other radiations as we learn them in the topic called radioactivity. So we understand it much better when you combine these videos together. I mean, this lesson together with the other lessons. It can also take place when electrons oscillate around the energy levels. So electrons they oscillate in the energy levels. So this changes their kinetic energy. So the change in their kinetic energy, which means the change in their kinetic energy release these radiations. So the greater the speed of oscillation, the higher the frequency. Where we said frequency is equal to the velocity over the periodic time. So the shorter the wavelength and the greater the energy, as we have discussed earlier on. So when they are orbiting in their energy levels, they emit these radiations. Whereas the greater the speed, the higher the energy which is emitted. So let's discuss in detail the types of electromagnetic waves. We have radio waves as the first ones. So radio waves, as we have said, have the longest wavelength in the electromagnetic spectrum. They are produced when electrons oscillate. How do they oscillate? Where do they oscillate? They oscillate in the energy levels, right? The electrons produce electricity which oscillates in the area or antennae. So the radio waves are used for transmission of sound and picture information in radios and televisions. So all those pictures we look at in TVs, the sound we hear in radios, we might observe that earlier on before the upgrade of the new radios and televisions, we are having radios with the antennae, big antennas, and even the TVs we're using an antennas. So those antennas are used to what? Are used to trap these radio waves. So they trap these radio waves and convert them digitally to prevent those pictures together with those audios in radios and TVs. Then we have microwaves. We are familiar with the microwaves moving light, whereas the microwaves are used for satellite communication and radar communications. They can also be used for heating food in a microwave. So a microwave oven, the food is heated because it contains water which is stronger and absorbs, which is a stronger absorber of the microwaves. So you observe that these microwaves have other thermal waves. What are thermal waves? They are the ones which emit energy, which emit heat energy as they travel. So the first one having microwaves, we discuss later, the other one later on. Then you have the gamma radiations. Gamma radiation is produced from transitions within the excited nucleus of an atom and usually results from some previous radioactive emissions. So the gamma radiations can also result from fission and fusion reactions or the destruction of a particle. So wherever an atom is being destroyed, there is emission of a gamma particle. Wherever there is nuclear fusion, which is just the what? The splitting or joining of one or more atom to form a bigger or a smaller molecule. That is nuclear fusion and nuclear fission. We will learn them in detail when we'll be looking at radioactivity or nuclear physics. So whenever there are these types of reactions, a gamma ray or a gamma radiation is emitted. So gamma radiation is used in treating cancer because it kills cells. Since its rays are more penetrating, as we said, they have the what? They have the shortest wavelength, which means they have the high energy. So they are also used for sterilizing food and medical equipment as they can also kill bacteria. So they're also used in hospitals for sterilizing medical equipment and treating cancer, where they kill the cancerous cells. Then also have the X-ray radiation in the electromagnetic wave. So the X-rays and gamma rays are not different much, whereas the X-rays are produced when fast-moving electrons lose energies very rapidly. So shorter wavelength X-rays are very penetrating. As we said, we can have shorter wavelength of X-rays and even long wavelengths of the X-rays. Mind you, we said the radiations they might interact with the other radiations or they might overlap with other radiations. So which means to say we can have X-rays of long wavelength and X-rays of short wavelength. So we're saying shorter wavelengths of the X-rays are very penetrating. Therefore, they can pass through dense metals like lead, which is a strong metal, right? So longer wavelength X-rays are less penetrating and can therefore pass through flesh but not through the bone. This makes the bones to show up on an X-ray photograph. So which means in X-ray machines they use what? They use the X-rays of longer wavelength. Why do they do this? This is the reason. And therefore pass through the flesh but cannot pass through the bones. That means wherever they are stopping at, they will form an image of the place where they are stopping in. Then you have the ultraviolet radiation, or also called the UV light most times. So ultraviolet radiation is produced when there is high temperature due to large energy changes in the electron of an atom. So this is another example of a thermoradiation. So the sun produces a large amount of UV light, so most of which is absorbed by the ozone layer in the upper atmosphere, and the remaining absorbed by our skin. We even feel the heat from the sun, right? So that is the ultraviolet radiation. So the UV radiation is used by our skins in production of vitamin D, although excess vitamin D is harmful and can even cause skin disease and damage the retina. The retina in the eyes. It is also used to cause fluorescence, which gives out visible light. So it causes fluorescence as we see the light in the during a broad daylight. So that light is because of the UV light which is emitted by the what? Which is an radiation emitted by the sun. So UV light are produced by what? Are produced by very hot objects. Even the what? Even the infrared radiation. They are also produced by what? By very heavy objects. So the infrared radiations is produced when there are small energy changes in an atom or the molecular vibrations. You can see how all these radiations are formed. It's all related to some changes in the atomic structures. As an object gives more infrared radiations as its temperature rises, which means and if an object is having more temperature, it is emitting what? It is emitting more infrared radiations, or meaning to say, very hot objects emit infrared radiations. So the infrared radiations is used to what? Is used in photography. It is also used by the Earth satellites to determine the health of globes. Then last we have the visible light, which is produced when an object is at very high temperatures. So it's another example of a thermoradiation. So at such temperatures, the objects become very hot and produce visible light. Visible light is used for photographic film, which is formed on the retina in the eye, and again even in the what? It can also be used in the what? In the camera. So as the eye in the camera works just like the same. And again, it's also used. It also causes photosynthesis in plants. So that's a brief detail of each type of electromagnetic wave in the what? In the electromagnetic spectrum. Then let's have a look over how we can detect these types of electromagnetic radiations. So it's just a summary of them. So in the left, we're having the what? We're having the name of the electromagnetic wave. On the middle, we're having their sources. Then last on the right, you're having their detectors. So the first thing first, we start with gamma ray, whereas we're having the sources. What are the sources? The nuclei of a radioactive atom, and even what? Cosmic rays. So these are the sources of gamma ray, whereas we have their detectors. What is the detector of a gamma ray? We have the gigamolar tube and the photographic plates. We have the X-rays. What are their sources? We have the X-ray tubes. How can we detect X-rays? We can use photographic plates or films and even the gold leaf electroscope. Then you have the ultraviolet light, which is also called the UV light. What are their sources? We have the sun, sparks, mercury vapor lamps, and very hot objects. What are the detectors? Fluorescent screens. So when you say a fluorescent screen, it's anything which produces light as long as what? As long as a certain type of radiation is passing through it. So the fluorescent is like the glowing thing, right? So whatever is glowing, that is the fluorescence. Then also have photographic films, which forms like an image when light passes on it. Then you have the visible light. What are their sources? We have the sun and the lamps. Anything producing light can produce as long as it's producing light, it produces the visible light radiation. What are their detectors? We have the eye in the camera. We have photocells and photographic films. We also have the light dependent resistor, which changes resistance when light varies when it's reaching the object. Then you have the infrared radiations, with the sources being the sun, warm and hot objects. So what are their detectors? Have a thermobile and a phototransistor. Microwave, what are their sources? You have the microwave oven, which is the common one. It can be detected by the waveguide tubes. Then you also have the radio waves. The sources have the TV and radio transmitter that uses both electric circuits and even what and the aerials. With their detectors again being the aerials, the diodes and earphones. That's how you can detect radio waves. Let's look at some experiment whereas we can be detecting infrared radiations. So we can heat some water in a beaker. This is an experiment, right? Heat some water in a beaker and transfer the water to a copper container. Connect a thermobile to a sensitive galvanometer. What is a thermobile? It's just like a screen with a blackened end. Why a blackened end? The blackened part it absorbs the what? Absorbs the heat from the hot object. That is to say, in this case, we're using hot water in a copper container. So bring the thermobile close to the hot water in the container as shown below. Then you have to observe what happens to the galvanometer. So this is the example. Having the what? Having the copper container with the hot water. So as you say, radiations they travel in a medium. So right now they are traveling in a medium. In this case, it can be air. And having a thermobile connected to what? Connected to a sensitive galvanometer. A galvanometer is an instrument that is used to detect small changes of current. So there's a recording on the what on the galvanometer. The meaning to say there are types of radiation which are being emitted. So what type of radiation is being emitted? We have the infrared radiations as it's emitted from what? From hot objects. So the galvanometer shows some deflections showing that infrared radiations have been detected from the hot objects. To detect infrared and ultraviolet radiations, another experiment. So the very first thing we have to set the experiment or the apparatus as shown, whereas we have a radioactive source when they are having a prism. A prism is like a glass. They are having a screen, though it's not labeled, but this is the screen. So this is the labeled part of the lights which will be emitted. Let's have a look at the procedures and explanations. Observe what happens on the screen. So you just arrange them as this, whereas you're having a slit with a small hole, whereas the radiations are just passing, like producing a single radiation. So observe what happens on the screen. Move a thermobile connected to a sensitive galvanometer towards the lead end of the spectrum and then into the dark region beyond the lead end. So move a thermobile. While using a thermobile in this case, we are saying this experiment can be used to detect both infrared and ultraviolet radiations. So if you are using a thermobile, which means to say we are what? We are detecting infrared radiations. Observe what happens to the galvanometer. Definitely there will be some deflection on the galvanometer showing that infrared radiations are what are being emitted. Then here we are saying move the blackened bulb of a thermometer towards the lead end of the spectrum. So this lead end of the spectrum and then into the dark region below beyond the red end and you have to observe what happens. So this is an explanation. An increase in the detector readings of the galvanometer and the thermometer when it is placed just beyond the lead end of the spectrum shows the presence of visible radiations called infrared radiations. So brightening on the photographic film. So this is a photographic film, the one which is appearing like a black line. So that's a photographic film. And the glowing of the fluorescent paint when placed just beyond the lead end of the spectrum, it shows the presence of visible radiations which are called the UV radiations or ultraviolet radiations. So these are the two experiments which can come out in this topic on how we can detect the particular types of radiations. Let's look at applications of electromagnetic waves. So these waves they have a wide range of uses in day-to-day life. So we're also having a table again, which is showing the electromagnetic waves and their uses. So here should be their use, not detectors. So we have the gamma rays. So what is the use? It is used in detecting flaws in metal casings. It is used for sterilization, as you have just discussed. It is used in medicine to treat cancer. So the last two are used in medicine. The first one is used in what? Is used in industries. We have the X-rays. They are used in radiography, radiology, detecting frozen metals, deflection to find crystal structure, detection of what and forgeries. All those things can be detected by the X-rays. We also have the UV light. It can also be used for treatment of skin complaints, killing bacteria, fluorescent lighting. It can be used in background lamps and automatic counting in industry can be used by they make use of the UV light. We also have the visible light. So the visible light is used for reflection, photography, and dispersion, which is the splitting into different colors. We have the infrared radiations, which can be used for cooking, heating, drying, photography, and even photocopiers. The microwave, as you have said, they are used for what? They are used in radar, communications, and microwave cooking. Lastly, we will look at radio wave, which are used in communication and navigation. So that's it about their uses. Then let's finish the topic by looking at the wave nature of electromagnetic waves. So since they are waves, they also obey the what? They also obey all the properties of waves, which we discussed in Form 3, whereas you have interference of waves and those other properties. So we have learned that all waves move at the speed of light in a free space, that is in a vacuum, at a velocity of 3 times 10 to the power 8 meters per second. We also learned that the electromagnetic waves obey the wave equation, which is velocity of the wave is equal to the frequency times the wavelength, whereas it can be written by the velocity can be written by the c or v, which is equal to the frequency f and the wavelength by this other symbol. So from there on, we can have some other calculations. So whereas we use two calculations in this case, the first one being Zodiac Broadcasting Station broadcast a wave of speed 3 times 10, yeah, 3 times 10, that should be power 8, I think, meters per second on a frequency of 1.5 times 10 to the power 6 kilohertz. Find the wavelength of this particular wave. So how do you solve this one? To solve any problem, first of all, you just have to look at the things which you are given. So what are you given? We're given the wave speed and the frequency, which means to say, looking at our formula which says velocity is equal to frequency of but read by wavelength, what's remaining is only the wavelength. So which means you have to reverse the formula and find the what? Find the wavelength. So we're having the speed of velocity being 3 times 10 to the power 8 meters per second, the frequency being 4 times 10 to the power 6 hertz. Here we are supposed to find the what? We're supposed to find the wavelength. So this is the formula, right? Whereas you're having velocity is equal to frequency times the wavelength. So what are we meaning with, or what are we supposed to find? It is the wavelength. So you can make the wavelength to be the subject, whereas you just have to divide by f both sides, divide by f, which will result into wavelength is equal to what? Is equal to velocity divided by the frequency, which is 3 times 10 to the power 8 divided by 1.5 times 10 to the power 6. At the end, you find the answer as 200 meters. So wavelength is measured in meters, the speed is measured in meters per second, and the frequency is measured in what? Is measured in hertz. Another example, you need a radio station emits radio waves of wavelength 300 meters. Calculate the frequency of radio wave if the speed is 3 times 10 to the power 8 meters per second. So it's just a matter of writing the formula first, then looking what's missing. So what's missing here, it is the frequency. So just copy whatever is in the question. The velocity or the speed is 3 times 10 to the power 8. The wavelength is what? The wavelength is 300 meters. What about the frequency? Looking at the formula, you make frequency to be the subject. Whereas when you make frequency to be the subject, it will be velocity divided by the wavelength. which will result to 3 times 10 to the power 8 meters per second being divided by 3 meters. Hence, you find the frequency as 1 times 10 to the power 6 hertz, not meters. So it should be 1 times 10 to the power 6 Hz, which means hertz. So that's it about the wave nature of these particular radiations. We finish by looking at the effects of electromagnetic waves. So the very first effect is greenhouse effect and global warming. We all know what a greenhouse is, right? So in a greenhouse, we use a glass that allows visible light and short wave radiations produced by hot objects to pass through. So we have a greenhouse gas. I mean a greenhouse where we are growing in our where we're growing in our plants. So as you are saying, it only allows what? It only allows visible light and short wave radiation produced by hot objects to pass through, which means the radiations produced inside the greenhouse gas, they have what? They have long wavelength. Why long wavelength? Because they what? They possess less energy and they transmitted at less frequency. And they're even cold, that's why they have the long wavelength. So whereas the plants cannot transmit the long wavelength given out by the cooler objects. So which means, so this is the diagram, whereas having the sun as a hot object producing short wavelength which can enter inside, whereas the long wavelengths produced by the plants cannot pass outside, which means this is what these short wavelengths are trapped inside, hence causing the greenhouse effect and the global warming. So the greenhouse effect and the global warming is just a matter of warming up the temperatures. Then you have the global warming. So the first one was about greenhouse. The second one is the global warming effect. So the atmosphere, just like in a greenhouse. So consider the Earth as the greenhouse. So the atmosphere allows shortwave radiations from the sun to pass easily to the surface, which warms up the ground. The warm grounds radiates heat in form of infrared radiations into the atmosphere, which are then absorbed by the atmospheric gases, which results in warming up the earth, as these radiations are not given out again from the earth into the what? Into the other part out of our atmosphere, which results to warming up the earth, hence leading to a global warming effect. So the first one was greenhouse effect, the second is about global warming effect. The other ones are we have the effects of the UV rays or ultraviolet radiations, as you have said, is comes from the sun actually. So it causes sunburn that occurs when skin cells are damaged by the absorption of energy. The effect of gamma rays. So these rays, when exposed to them, they may kill body living cells, which might cause cell mutation, which we learned in biology. Whereas it results in what? Sudden changes in the genetic makeup of your cells. So the effects of X-rays. So the X-rays can cause cell mutation. For example, we are looking at DNA changes. It interferes with what? The makeup of the cell tissues, I should say so. They can also cause skin cancer, which is the abnormal growth of living cells. X-rays can affect childbirth in the way that the rays can lead to deformity in the infant. That is, if a mother is carrying a child and is passing through an X-ray, the rays, yeah, an expecting mother, I should say, the rays can cause baldness, which is the loss of hair in the head. So these rays may sometimes cause baldness, that is the loss of hair on the head of a person. Reaching this point, we have finished our topic of electromagnetic waves. Thank you for watching. Hope you enjoyed the lesson. See you in the next lessons.